Hello, everyone. In this episode, we'll run the same synthetic stock returns using GAN as a GAN application, but with using Wasserstein GAN. So, since the previous episode 17A, where the GAN had mode collapse, with the help of Claude, Anthropic Claude, I iterated on improving the GAN structure to make it more workable and have more successful results. So, I'm going to share that with you. Okay. So here's using Wasserstein gun. So instead of real and fake indicator from the discriminator, we call it now critique in Wasserstein gun, will give a score of in a continuous version of how real it is, um, which makes the gun more stable. But also the parameters have been more adjusted and many things are done um, in the vanishing gradient. So uh, long story short, here we repeat this. So we load still the same data, and so the SMP um, here, pretty much this part is the same as the 17-A. We prepare the data, but now we build Wasserstein GAN network. And what you can see is that, well, the generator still generates from random seeds some um, data that are fake output data. But um, um, yeah, so but the output is having some output dimension in this particular case. That adds a sequence of output stock returns. And then the critic is 1, but this is now a continuous number, basically. So this is the structure. And the key difference is that, like here from the standard gun, it's a linear scale of the discriminant output, and the Wasserstein distance, which is different from binary cross entropy. And the generator have layer normalization and some custom training loop with gradient tape. Um, and the critic to generator update here, so it's 5 to 1 because the learning rate of the rate of learning for critic and generator differs. And if one becomes more dominating, overwhelming, then the learning stops for the other one. So, which is why you need to actually play and balance it out. Okay. So here's the gradient penalty that we impose. And well, generator and critic loss. Uh, well, that's a standard Wasserstein gun kind of thing. And we have, again, uh, critic updates 5 times for every one generator update. So the critic needs to be a good estimate of Wasserstein distance before the generator takes a step, basically. Okay. So these are all helper functions and train the critics one step and the generator. So and then now we go. And it turns out that we don't need really 20,000 or that many epochs, so well, just 5,000 and we'll evaluate every 1,000 epochs. Um, but at the end of the day, it's very similar, isn't it? We update the critic and then the gun and keep recording that. So here is actually a progression that's probably informative to see. So it was actually not too bad after 1,000 iterations. It's already starting to emerge, and the gradient penalty is actually 0.01, which is pretty good. Um, but as we move on, it really becomes here. Look at the epoch 4,000. The real return and the gun generated return, W gun generated returns are fairly similar, isn't it? Yeah. So. And then you can run various diagnostics, the critic loss, and they all are fairly well converging. Initially a little bit oscillation, but it's getting really good. And then evaluate the generated returns. So for the real and synthetic, um, basically it's case statistics. That could be smaller, but it is already a fairly good value. Um, and visually comparing it like the real and synthetic distributions uh, of the CDF uh, or synthetic quantiles are fairly similar, isn't it? Yeah, it's almost on the 45-degree line. So synthetic price path simulation, so that's one application. So if you need to have a Monte Carlo simulation and there's only one real world path, but can you generate some others, then hypothetical for some VAR computation or many other things, here is something. And also value at risk estimation, where you need many scenarios to estimate um, um, the possibilities of going very extremely wrong. Um, so that, um, and with the historical estimate and with the GAN, basically, you can see here the estimates for historical and GAN are fairly similar, especially relative to the normal assumption, where the real distributions are more fat-tailed. The GAN generated data gives are fairly close to what historically has been, and you can see it here. All right, so all in all, um, what you saw from the earlier episode that the gun could fail, and here is an example of how you remedy these kind of things. Okay. Thank you for watching this episode.